So we ended with the linear level curves here. Yeah. So we had just started with the L-shaped. Consider now L-shaped level curves as depicted in figure 2.10a. For example, suppose we want to produce bronze Y by mixing tin X1 and copper X2 to produce 100 grams of bronze. Suppose we need to mix exactly 12 grams of tin with 8 grams of copper. This kind of technology gives rise to L-shaped level curves, as you can see in figure 2.10a. So we have the point x1 equals 12, x2 equals 88, results in y equals 100, and the point x1 equals 18, x2 equals 88, results in the same y equals 100. By moving from x1 equals 12 to x1 equals 18, we were not able to produce more y because we do not have extra x2 to mix with x1. In some sense, the additional 6 grams of tin are wasted because we cannot produce more bronze with it. If we had more of both variables, x1 equals 18, x2 equals 132, we could produce y equals 150. Note that the kink of each L-shaped level curve corresponds to optimal mixes of x1 and x2. At every kink, we maintain the targeted proportion of 12% of tin and 88% of copper. Hence, there are no wasted resources at the kinks. Consequently, so if you slowly go over this paragraph, we can kind of, fast forward the video, rewind it. They're talking about these things here, but those are the L graphs, and the corners, of course, are the kinks. Yeah. Consequently, if we want to maximize y subject to a constraint on how much x1 and x2 we can use, say that right there, yes, 100 is greater than or equal to the addition of them, then naturally our optimal choice must be at the kink, and we must be using as much x1 and x2 as possible, given the constraint. The optimal choice A in figure 2.10a represents exactly these two features. Yeah, so there's A, they have the constraint line, and obviously it's just going to be wherever it intersects there. B has an interesting constraint line going on, but A is pretty obvious. Yes. So they have the condition 1 and condition 2. Yeah. When working with L-shaped level curves, the optimal choice must be at the constraint line. We need to be at a kink of a level curve. At this point, you should be asking, how do I know that a point is at a kink of the indifference curve? To answer this question, we need to use, I didn't really catch it with C1 and C2. We need to be at a kink of a level curve that's C2. The optimal choice must be at the constraint line. Yeah, every single, yes, every single one of these graphs, the optimal choice, the maximum has to be, remember the maximum, we're looking down from a bird's eye view. So the maximum is a three-dimensional graph. Maximum is always on the constraint line, and we need to be at a kink. So it's kind of silly because it's very obvious here. At this point, you should be asking, how do I know that the point is at a kink of the indifference curve? To answer this question, we need to use information available about the optimal mix. In our example, we need 12 units of x1 for each 88 units of x2. Cross multiply the proportions to find the optimal mix. We have that little equation right there. That's how they get that. The following two interpretations help us understand this condition. If we rewrite the optimal mix as x2 over x1 equals that, it tells us that the two variables should be used in a ratio of this right here. Yes, x2 divided by x1 equals that. If we rewrite the optimal mix as x2 equals this, we have a straight line. They got that from just a ratio, yes. x2 over x1 equals the two values, the slope, the ratio. We have a straight line starting from the origin with a slope of this. This is a red line. Yes, so they do all of that to get that red line there, yeah. And every point on that red line is at a kink. If we rewrite the optimal mix as x2 equals that, we have a straight line starting from the origin with a slope. This is the red line. Note how the red line crosses the kinks at level curves. This is why this equation guarantees that we will with the kink of the level curve. The optimal mix equation represents condition 2. Condition 1 is simply the constraint line. We can solve this system of two equations and two variables to find an optimal choice, yes. We don't necessarily need the graph, it's simple as that. Okay, so recapitulating, condition 1 applies to all three cases and is simply stated that in our economic application, the constraint will be binding. Condition 2 tells us what is the optimal mix between x1 and x2. In the case of strictly convex level curves, the optimal mix is at a point in which the slope of level curves equals the slope of the constraint line. They are tangent. This is just reviewing everything. In the case of linear level curves, yeah. So it's just kind of reviewing. Sometimes if I scroll a little bit, this course is supposed to be two things. We're supposed to be actively learning, and I know it's a little bit silly, but we are just kind of reading the entire book from beginning to end. So if we scroll, we can kind of choose how much we read. Although we will focus on these three cases in this book, so it's good news. The Cobb-Douglas, yes. The linear level curves and the L-shaped, those are very common throughout this book. There are other cases that might be relevant in certain economic situations. So we have to get creative, but it's all kind of the same thing here. You know, our straight line, we have to know a little something about. In my opinion, the black there, the black lines, those are the contour lines. We have to know something about what the contour lines look like, and that's very, very easy. Yes. Can we kind of see the algebra in our head, even if you have a very complicated graph? You just set y equal to a number, and then you get a contour line, even if we don't know how to graph it. But then you have a constraint line, yeah? And the point of intersection for anything is always going to be the maximum. It's almost kind of silly to go through 10 videos when all you have to do is do the contour line, the constraint, set them equal, find the point of intersection, and that's the thing. So basically, if we want to just kind of carefully go through whatever explanation they're giving. Yeah, so we can basically skip all of this. It's just going to be another example. That's interesting. So the contour is linear, but the constraint is a curve there. Okay, so this is what we're going to do. We're not going to do elasticity right now. We're going to do that soon. If you recall before, we had the homework and there's just a little bit, the most important problems at the end we did not do. It's because it involves maximizing these constraints. So in the next video, we're going to start tackling the end of that homework. After the homework, then we're going to get into elasticity here.